w to the n equals z naught. So z naught is a given complex number, and you solve this equation. If this is a real number equation, how do you solve this equation? I give you z naught becoming 5, and you solve w to the 4th power. How do you solve this equation? You put maybe a radical symbol and put plus minus, and that's how I teach in the pre-calculus, right? But it gets a little bit more complicated here. A whole lot more Freudians kicks in. So we're solving this equation, and first thing you do is that you write z naught as, what is it? What is this thing called? Polar form, right? You write as a polar form. Then it seems like writing down all the solution is very straightforward. So how would you solve for r0 and theta 0 if it is in general? We have to use a calculator. You know arctan, and you get all the decimal numbers to get that, right? All right, that's the first thing to do, and here's a complete solution. The wk. So, well, let me give you a simple example to, how about w to the n equals 1 plus I. Does it look like an equation? W to, let me go ahead and change that to w to the 7th power. Sorry about that. So everything is given except the w. Now it looks like an equation, right? Does it look like a polynomial equation? Unknown is w and raised to the 7th power, and its constant term is not 1 plus I, but negative 1 plus I. If you move it to the other side, it looks like a complex polynomial equation, right? So we're solving degree 7 polynomial equation. Okay? So according to the fundamental theorem of algebra, do you know how many solutions are there? Full 7 solution. Sometimes they're repeated roots, but you'll be able to find full 7 solution in that. It factors completely into 7 linear factors, potentially repeated roots. What are those roots? 7 roots. And here are the 7 roots, wk, right? What do? So you know r0, r0, is a positive number, modulus, right? So we have no problem of putting the kth root in there, right? You can't do that if r0 is a negative, but modulus is always a positive. What happened to argument side is that it's going to be theta k I times theta k. It's a little bulky, so I'm separating the theta k part here. Is that right? There are going to be 7 roots. They're all indexed by this k. Modulus is all common. r0, 1 over k. I'm sorry, this is not the 1 over k. What is the correct number? Not the k. Nth root, right? So it's 1 over n. Sorry about that. It's nth root. So you put that nth root, and that's what happened. 1 over n. So modulus is all the same. There's no k. As k varies, it's always the same. But here's a k. Is that theta 0 plus 2 L pi. Let me do that L pi. No, the k still works, I realize. Sorry about this. K still works. K pi divided by n. Where k runs through 0, 1, all the way up to n minus 1. Although it ends at n minus 1, we start from 0, so you can see I'm talking about 7 statement. W0, W1, all the way up to W6, if it is the case. Right? So that's how you solve it. So we're going to get used to the statement first and think about whether it's true and how to discover and improving things like that. All right? So I'm going to do that in the Mathematica and showing you handle some of these bulking, repeating seven times. So this Mathematica is convenient. In the Mathematica, so I hope we can do this quickly enough. Several things. I'm going to first, can you see that? As you know, is 1 plus I. I'm doing that example, and that's how you type a complex number in Mathematica, right? And for some reason, if you want to do vector form And this is how you actually separate the vector form. If I have a and b, I'm assigning this, the real part of that z0, that works. And it's going to pick 1, an imaginary part, z0, and it's going to pick coefficient in front of I. Okay? So if you do that, and a and b is now a is 1 and b is 1. Right-hand side turn into a vector, and at the same time is assigning to a and b and all things like that. So if you want to turn complicated coefficient into a vector form like this, and this is the way to do it. And I'm going to use it to plot this complex number in the xy plane. I want the vector form. Next thing is that I think so. Here, let me introduce creating a list. If you want to type a list of 4 numbers like this, and it's going to be a list, and then here is home, and it's going to be my list. Usually, the things that start with a capital is reserved for built-in command, so I'm using a lowercase in here. So that's going to be a list, and you can pull out 1 and 2 and 3 and 4 at the same time. But you can imagine a more complicated and more longer structure you don't want to type in. So I'm going to create the list automatically, and here's the command, the table. Table is a way to generate it here. And usually there's a formula in here in terms of k. That's what we're doing in here. So k runs through 1 through 4, for example. Let's say 10. K is going to run through from 1 to 10, increased by 1. And if you write down some formula in here, it's going to generate. For example, if I do 2k minus 1, then it's going to generate k, plug it into 1 there and 2. So what kind of number is that, 2k minus 1? These are odd numbers, right? So it's going to generate odd numbers in there. And if you know what it is and don't want to see what's stored, and then if you put a semicolon, it doesn't show that the result. You just assign it, and that's it. So that's that. Let me show you one more thing. You see that k changed to a little dimmed bluish cyan color, right? It means it's a local variable. So let me show you this. If I assign k equals 1 in here, k is going to be 1 for from now on. But if you still want to use this k as a local variable in program, it's very simple programming, right? K runs through 1 through 10, and it's going to recognize automatically. Let's say I'm going to square that this time. K going through 1 through 10. This time jumping by 2, not by 1. So 1 and 3, and it's going to hit 9, and it's going to skip 11, but it's exceed 10, so it's going to stop right there. So if you add one more number, it's going to be increment. Does that make sense? So when you do that, k is not going to be 1. It recognizes command k is going to be local variable. So for the moment, when it's running this table command, it'll forget k, use its own variable, local variable. That's the idea of a local variable. K equals 1 out there is a global variable. As soon as I hit it, k now changed to black in the first line. So mathematically remembers k is 1. But just for that command, table command, it's going to be local, right? This idea of declaring the local variable is important when you write a little script. If you want to do repetitively, you declare that your favorite names of a variable, so you could use it again and again. But in this case, it did it automatically for us because that's the structure of the command. Okay, so that's the one thing. So I'm going to write down. First, I'm going to calculate. So let me go back to this guy, and here. And our z0 is 1 plus I, right? Correct? And I need to calculate the modulus. I need to calculate this theta 0. Then I'm going to create this theta k, right? You have to repeat it 7 times. And then I'm going to use this table command and things like that. So let's go ahead and calculate R0 first. So what's R0? You can do it in one sentence like that. And theta 0 is going to be like this, th0. All right? So what is R0? In Mathematica is the absolute value, okay? And you know it's 1 plus I is already in where? First quadrant, right? So arc10 will be the answer. If it's a fourth quadrant, arc10 is the answer. If it's the second and third quadrant, you have to add and subtract pi, right? So what is that? It's arctan of, what is that? B over A. I define it as a B over A here, right? B is the imaginary part and A is in imaginary part. Is that right? So B over A is going to be assigned as R0 and theta 0, correct? So let's see. So we calculate in the exact fashion. But if it is not special value, it's going to be a decimal number. But you can turn this one into decimal number using the command n, capital N, or a nice trick I use is that one dot is at 1.0 multiplied to this ABS, and it turned to a decimal number. And I'm going to keep it as a decimal number. Is that right? So if you do that, it gives you 1.41 in decimal, and it's 1.0 multiplied to that. So we got that. Okay. So what is R is going to be? The modulus for our W, right? Anybody remember the formula? Formula here is that the modulus of our solution does not depend on K, right? Not depend on K. So the R0, the seventh root. That's what that is. So it's going to be R0, seventh root, it goes in like this, 1 over 7th. Okay? So that's good. That's going to be the same modulus for all 7 solutions. Okay? How about the angle? Sorry about that. Better use this one. I feel retarded. All right, these are the angle. Okay? So we have to figure out that angle. Angle looks like this. We already know theta 0, right? And we have to vary this k from 0 to 6. Is that right? 0 to 6. And create all those values. That's what I'm going to do. All right, let's see. How do you create a list? It's going to be a table, right? The table, and there's going to be a formula of that shape, but how does the index go? K going from 0 to where? 6. So it's going to increase 0 to 6. You're going to repeat that for the formula again and again. So if you do control slash, it gives you a nice fraction form. It's very convenient. So how does the numerator look like? Numerator here is the theta 0, right? Theta 0 is the arctan that we have calculated already. So there's a theta 0. Is that right? And plus, how does this remaining part go? 2k pi, right? 2k pi. So it's going to be 2k, and pi is a capital Pi. Have to be capital. It's a recognized built-in command. Or if you do this escape key and P and close escape P, and then it recognizes also pi. Because the theta is 0, I'm assuming that it's going to turn everything to a decimal number. But try to keep this pi in there. What was the denominator? Remember? Was n. That's the power of this equation involved exponent. So that's 7 there, right? So that's going to generate this numerical number. These are arguments, right? The first angle is a 0.1 radian, and second one is a 1 radian, third one is a 1.9 radian, things like that, right? So we want to use this when we pull out one at a time, so we better name it. So I'm going to name it as a list of a theta, and then we can use the list of a theta. Okay? So we're going to pull out one element at a time and generate complex number. That's what we want to do, right? Pull out one angle at a time and consider this number. That number is the solution. That's what this statement is about, right? Okay, so that's what we're going to do. This is how you do it. A very convenient way of doing in Mathematica is that it's a map. This is the action part. Okay? This is the action part, and we're pulling out from list theta. We're going to pull out each number from list theta at a time and do something in here with that each of the number, and then it's going to be another list, right? Each of these item from list theta is represented by the sharp symbol. And at the end, you have to use this, what is the name of the symbol? And symbol? What is it called? Ampersand is complicated, so I'm going to call this AND symbol. AND symbol. This is a way of, in mathematics, a way of writing a functional procedure on the fly, on the go, right? So you don't have to name this thing. So what's it going to be? You pull it out and do nothing and just display this thing again. Okay? So that's going to be exactly the same list, right? We didn't do anything. Pull that out and do that. If I multiply by 2, then it's going to multiply everything by 2. So each number is pulled out from the list and do this action of 2 times and generate this corresponding list. Does that make sense? It's called map. Very, very useful and convenient. But what is it we want to do? We want to take that argument and turn it into complex numbers, right? What is the modulus of this complex number that we want to write down? Here. Modulus is R0 1 over n, right? We named it R over there, but you can type R0 1 over 7 directly in here. But I conveniently named it R, right? And how's the rest of the part go? That's the new modulus, shrunk modulus, and then you have to write down this trigonometric part, right? Trigonometric part goes in there. So here's a cosine plus sine. You have to use a bracket in Mathematica. So does it look like polar form now? R is previously defined. You have to choose the argument. What is the argument that we're plugging in here? They're all coming from the list, right? So what is the symbol to represent those? Or the shop symbol there, right? Shop symbol. And you have to put that AND symbol to close the parenthesis. If this procedure you're going through is as simple as this is a very good command. If it is complicated, you will define that procedure with a different name, and you can call that name, and I'm going to show you. All right? But if it is simple as this, it's a very useful command. Now, if you do that, it's generating this complex number. Fixed modulus and changing the argument, they generate all these seven different complex numbers. Make sense? Okay. So how are we going to verify this one? So let's call that one. Is that solution list? Is that a good name? So it's going to be solution list. So we have all the 7 solutions for that equation, right? So how are we going to verify these other solutions? What do you want to do? So Alt 7 to text mode. Let's check. Okay. So we're going to take that, each of the item from the solution set. What do you want to do to check if it is the correct answer? So we're going to do some sort of action. Where is this coming from? Our solution, right? We're going to take that each of the element solution, which are complex numbers, right? And then we're going to do some sort of checking procedure. What do you want to check? These are supposed to be solution of what? This equation there, right? So what are you going to do? You're going to raise the 7th power and see if it is really 1 plus I. If it is a solution, you raise the 7th power, it's supposed to be 1 plus I. Is that right? Okay. So that's what I'm going to do. So what is the action that we're going to do here? Sharp? What are you going to do about that? Raise to 7th power. Right? So it's going to be a list of 7 numbers, and what are they supposed to be? All 1 plus I, right? Which didn't do. Do you know what happened? Oh, the n. Thank you. Yeah. So we got 1 plus I, all the coefficients at 1 point because it's approximate solution. Sometimes it gives you some long number multiplied by 10 to the negative 26. What's your interpretation? That's 0. But sometimes it does that, right? So, all right. It's a good sign, right? Okay. So here's the one thing we're going to do. We have these solution, right? And we want to plot those in xy plane. Then you have to change the vector, remember? Right? To plot it. So I'm going to take each of the solution and turn it into a vector. Remember how to do that? So vector look like this in a complex number. I mean, in Mathematica, x component and y component, right? So what is the x component of a complex number? How do you write it in Mathematica? Real part? Real part of the complex number there. So pick out a complex number, and real part and imaginary part goes in there. Does that make sense? Does it look like a complete procedure? It's pink. It's a sign that it's not good, and to that now it's a variable and more greenish. So take the complex number, real part and imaginary part goes to this point like that. So this is going to be list of points like this, right? And it's because it is a traditional form, it looks like this. But and those are, you can see x part and y part in there, right? Okay, so I'm going to do, I think it's called standard form. Then it does like this. Right, so here's the x quotient, and it's a list of points again. So there's a 2 braces there, right? Okay, so I'm going to do list point. So I named it. So you remember how to plot these several points? Anybody remember that command? Was a list plot, right? This has to be the list. Braces and brace again, but this whole thing is a list now. So you can just type it in there. And then it's going to sketch. It's not going to sketch. Why is that? Pairs of a number. Do you see what went wrong? Dang, I forgot to record it, but it is. We just fixed it. So I'm going back in here, and so let me explain a little bit about this one. So that's our first solution right there. That's our W0, remember? So if you do the W0 to the 7th power, what happened? So 1 plus I, that's what it's supposed to be, right? Where is 1 plus I? 1 plus I is right here. That's our target, right? So if you raise the 7th power, what's the geometric thing is doing the 7th power? You're rotating 7 times, right? With that exact angle. So here is our target. If you copy 7 times clockwise, you will arrive at exactly there, right? And what happened to, if you raise the modulus, this length to the 7th power, it reaches that length as well. But, and this one is saying, this angle here is divided into 7 pieces. And that's exactly the 1/7 of it. Okay? But it's also claiming that this one here, if you do it 7 times, you also arrive at here. How is that possible? It's too wide. So by doing the 7 times, you end up at rotating 1 time and arrive at here. If you actually copy it 7 times, you pass the 2 pi and back and arrive in here. Okay? And that's what this k equals 1 is about. There is 1 rotation involved. Okay? And this is the second root. This is coming from when k equals 2. So if you copied 7 times, what happened? Eventually rotated 2 times, right? And coming back to this 1 plus I again, and so on. So what if the last one is here? If you raise that complex number 7 times, how many rotation? The last one is involved 6 rotation, 7 minus 1. So if you copy it 7 times, it involves 6 rotation and coming back to it in here. Okay? So those are 7 complex number within that 0 to 2 pi. But if you raise the 7th power, the arguments is get large, then coming back to 1 plus I eventually. That's what's happening. And these are the 7 complex numbers. Where is it? Here. So let me show you the one more thing about, since we have just about 2 minutes, I think it's the right time to do that rather than going to anything else. So this map and a procedure. So for example, where is it? What did I do? Oh, here. If this procedure in here is too complicated, and you can call that procedure something else. So I'm going to show you list theta is a number. So I'm going to call that procedure 1. If I have a complex number z, so this is how you define a procedure. And the name of a procedure f is like a mathematical function. Inputs are listed here like the z underscore, and then recognize that these are the global variable, input variable. and enter. And here's a module. And this is where you declare the local variable. If you still want to use a and b in here, it's a convenient letter. But a, b was defined earlier. So if you declare it here, I'm going to use a and b. Then now it's a local variable. Now enter again. And you close it, whatever you do, and then close it a module. And that's how you define the procedure. What I'm going to do is that a is going to be real part of the complex number, and b is going to be imaginary part of a complex number. So a and b are real and imaginary part. And after you do all that, what is that going to be? The return value is going to be ab. I'm going to return a and b, like that. And it's end of the program. You go through all that intermediate procedure and return an a and b. So if you run this one and f of 1 plus I, what's that going to be? The vector 1, 1, right? So if it is long and complicated, you can call that entire procedure by f there, right? So I'm going to do that. The list theta, not the list theta, the solution list, right? So it's going to be map, and they're coming from solution list. These are all 7 complex numbers, right? And I want to separate the real part and imaginary part. That was simple enough, so I used that sharp symbol and did it here. But if it's complicated, you name it f, and the name of the procedure you define f is gonna do it in here like this. Do the same thing. Okay? But if it's simple, you can use a sharp symbol and an end symbol, like that. And also, if it is very simple program, just like that one, you can just don't have to do the module. If it's very simple, what I'm going to return is that I can write in a one line like this. Then you don't need modulo anything. It's just going to do it like this. But if it is really programming, computer algorithmic programming, and then you want to do module structure and do all that. Okay? So that's it, and I'll see you on Tuesday. Enjoy. There's a break, right? September the 1st is national holiday, and there's no class. Isn't that wonderful? There's no class.